Okay, so today we're going to go over slope fields. And over here is an example of a slope field. So you can kind of think of it as a graph because it may be small, but there are numbers here and here. So a lot of times it's a lot like labeling your coordinate plane. And along the axes you have these numbers, etc. Okay? And what we're basically looking at is a way in which we can see the equation of our function from solving a differential equation. Okay, so a differential equation is one in which you see the derivative. Now we all know the derivative, okay, is the slope of the tangent line. So a slope field actually draws in what the slope of the tangent line would look like. So for example, if the slope of your tangent line is 0, then you're kind of seeing horizontal line segments, okay, for every x value where the slope of the tangent line is 0. Okay, I'm kind of sticking to the same x values. And you can kind of see that that's what's occurring here. And then they're kind of steep over in this section. So that means that, or actually less steep. Steep would pretty much be more vertical than anything. I should say less steep. So maybe something like 1/4 or 1/2 or something to that effect. And you kind of have to draw it out the best that you can, what a slope would look like just with being a fraction of some sort. One is always really easy to draw in, I think, because it's just a complete diagonal going up from left to right. So something like that. And more steep would be something like if it was 2 or 3, something like that, and you had to draw it in. So if, let's say, this is 2, maybe make 3 a little bit straighter, and so on. If you had to do 4, make it straight, 5, maybe then make it a vertical line. But you kind of just drawing it in the best that you can. And it creates this kind of curve. So what it shows you is a direction. Sometimes it's called a directional field, of which your solution will be graphed. So our solution looks something like the ln of x. Okay, so perhaps maybe that is our equation when we solve our differential equation. Some differential equations we're not going to be able to solve for. We learned how to solve for separable ones. So sometimes our slope fields are really super important because we're not going to be able to solve for them. So let's get to an example problem where we can draw a slope field since they're that important and useful. Okay, so what you may be copying over here is, yes, the slope field is a directional field. I described that before, and it's based off of your differential equation. And we have a plot of short line segments. Describe that, kind of did a little for you. Okay, for a lattice of points x, comma, y in the plane. Okay, and y happens to be like our dy over dx. So that's why we're taking a look at this example here. So copy it down. And let's figure out what tables we can draw for each x, y. Okay, because sometimes y isn't our slope of our tangent. It was in the last one, but not for all of them. So let me point it out to you. Let's go. Okay, so when you make a table, you need x, y, and dy over dx. Okay, that way we can change different values. So dy over dx is dependent on what you plug in for x and y. Okay, so I could plug in any values for x. It actually doesn't matter what values of y I plug in because there is no y. But if this was dy over dx equals xy, obviously it's going to change my answer because I can plug in values for y. Okay, so kind of keep that in mind when you're doing these. Okay, so let's make a table, and we'll go with easier values first. So when x is 0, let's say y is also 0. That doesn't make any difference because when I calculate dy over dx, it's whatever x is, and that's 0. Next, let's say I make x 1. I can keep y as 0. Then dy over dx is 1. Okay, let's change some more. When x is 2, I can keep y 0. dy over dx is 2. Okay? And I can keep going. And fill in more and more values based on what I want to look at. I can make negative values in there, and so on. I'm running out of space in my table. Let's make a new table. And in my new table, maybe I want to continue and do a -3. So at least I'm getting all the values along my x-axis. So now let's say I want to change the y. If y is 1, that still makes dy over dx 0 because it doesn't matter what y is. So I can kind of plug in a y if there was a y and figure out a new value here. It's not going to be so new because it's whatever the x value is. Let me do some more so you see. Now, since it doesn't matter what y is, there's a sort of pattern that occurs when it's just an x that's over here. It's that vertically, and that was the word vertically, I will try to write it. They're all the same slope, vertically. So if we had just a y, horizontally, it would be the same slope, okay? So let's try to actually plot some more. I just want to emphasize you can change the values of y. Just in this particular example, it does not matter, okay? So I can make the y a -1. My dy over dx is still the same, whatever x is. So that's why we still see this pattern. Okay. So let me do my best to try to draw this out. So it's very much like graphing. Okay, and we get to fill this in. Okay, so when x was 0, our slope of our tangent lines are 0, so you have to draw in horizontal line segments. I tried changing the color so you can see the difference. Okay, when x is 1, okay, and it didn't matter what y was, then dy over dx was 1. So it looks something like this. Just have fun with it. Okay, guys. So something happened when I was recording, and I continued to do the graph here. Let me make this a little bit neater. Okay. When I finished all the slopes of the tangent lines, and again, have fun when you're doing it. Okay, so I did the negative slopes. When the slope is -1, then draw a nice diagonal line going down from left to right, and then just make it steeper and steeper. I then showed it is a directional field. So before we kind of looked at this being maybe some log equation, now if we connect these as slopes of tangent lines, then we can kind of see it's a parabola of some sort. If you did solve this differential equation, you get y is equal to 1/2 x squared plus c. So depending on what your initial value is, depends on where your parabola is falling, okay? So if let's say it was at 0, 1, it would be the green parabola that I was trying to draw in here. Okay, and so it would be y equals 1/2 x squared plus 1, and, well, you can see it is indeed that green one. So it is a directional field. It gives us direction of our graph, and you don't have to be perfect with those slopes, but get them somewhat right, okay? Just try to have fun when you're doing it, and let me know if you run into any trouble. Good luck.